Hi, and welcome to the last episode of this season on the Kalman Filter. Here we will give an alternative interpretation and derivation of the Kalman Filter. We will first describe the maximum a posteriori Bayesian estimation methodology. This will allow us to study non-linear estimation methods, such as the moving horizon estimation method. And this will be applicable to non-linear and constrained systems. This lecture will be a three-act play. We start with the maximum likelihood estimation method. Suppose a random variable y has a density function py, and this depends parametrically on a scalar or vector parameter theta. For example, if y follows the normal distribution with parameters mu and sigma squared, the parameter vector of the distribution is theta equals mu, sigma squared. The objective here is to estimate theta from n independent samples from this distribution. For example, a coin has probability p to land heads and 1 minus p to land tails. We toss it n times. How can we estimate p from our observations? The number of customers entering a store on a particular day is known to follow the Poisson distribution with parameter lambda. We observe and record the total number of customers on n different days. How can we estimate lambda? The wealth of people in society can be modeled by the Pareto distribution with parameters alpha and xm. We randomly select a sample of n people and record their wealth. How can we estimate alpha and xm? We ask, what is the most likely value of these parameters given the observed data? In general, a parameter theta, which is drawn from a set big theta, needs to be estimated from independent samples yi, for I goes from 1 to n. And these yi follow the same distribution with a PDF p, which is parametric in theta. In such cases, we can use the maximum likelihood estimation methodology. Suppose that the random variables y1, y2 up to yn are random samples, that is, random variables, with a density function p and parameter theta, and theta is drawn from a parameter set big theta. We start by defining the likelihood function, which is exactly the same as the joint PDF of y1, y2 up to yn, but seen as a function of theta, and treating the y's as parameters. The maximum likelihood estimate of theta is a maximizer of the likelihood function, if one exists. It is often convenient to work with the log likelihood function, which is the logarithm of the likelihood. This is denoted by little l. The maximum likelihood estimate of theta, given the data y1, y2 up to yn, can be written as a maximizer of the log likelihood function. Typically, we assume that the samples y1, y2 up to yn are independent. If that's the case, the likelihood function, which is nothing but the joint PDF of these y's, seen as a function of theta, can be written as the product of all PDFs. Therefore, the log likelihood, that is the logarithm of the likelihood, is the sum of the logarithms of all these PDFs. This is why we use the logarithm in the first place. It is because it maps products to sums, and sums are easier to work with. Let us now see how we can use the maximum likelihood estimation approach to estimate the parameters of normally distributed independent samples. Suppose that the samples y1, y2 up to yn are independent and follow the univariate normal distribution with an unknown mean mu naught and an unknown variance sigma naught squared. The parameter we want to estimate is theta equals mu, sigma squared, and the parameter space is this. This is because mu is a real number, whereas sigma naught squared is non-negative. The maximum likelihood estimate of theta is a maximizer of the log likelihood function little l with respect to theta, which is drawn from big theta, from the set big theta. Given that the samples are independent, the log likelihood function is equal to the sum of the logarithms of all density functions. Take a moment to verify that this sum can indeed be written like this. In order to determine the maximum with respect to theta, we need to differentiate with respect to mu and sigma squared. Actually, we are ignoring the fact that sigma squared must be non-negative and hope that the estimate we will determine will be indeed non-negative. Of course, we have to check that this hypothesis checks out at the end. The derivatives are given by these two formulas. By setting the derivatives equal to 0 and solving for mu and sigma squared, we obtain the maximum likelihood estimates of the mean and the variance. The estimate of the mean is the arithmetic mean of all observations, and the variance estimate is the arithmetic mean of the squared differences of all observations from the estimated mean. Note that the estimator mu hat, which is an estimator of mu naught, is unbiased. Indeed, the expected value of the estimator is exactly equal to the true value. On the other hand, the estimator sigma hat squared is not unbiased. The expected value of sigma hat squared is n minus 1 over n times the true value. You can show this as an exercise. Nevertheless, the estimator is asymptotically unbiased, which means that although the bias is not equal to 0, it converges to 0 as the number of measurements goes to infinity. You can show that the maximum likelihood is given by this formula, and the Hessian of the log likelihood function evaluated at the maximum likelihood estimate is negative semi-definite, and as a result, the maximum is indeed attained at theta hat. You can also derive these formulas that we mentioned previously, and you can apply the maximum likelihood estimation procedure to estimate the parameter lambda of the exponential distribution given n independent samples. So this concludes the first act. In the next video, we will combine the maximum likelihood estimation method with Bayes' theorem.